it's actually assuming you plug it in to a standard 120 volt outlet, and you can work out, I don't have it handy, but you can work out the inherent resistance of a 100-watt light bulb. I will point out, by the way, that the voltage here is fixed by the wall. If you actually increase the resistance, what happens to the power? It goes down. So what you have is, if you buy a 50-watt light bulb, that actually has more resistance, so it is less power. So a 50-watt light bulb is a bigger obstruction, and so therefore it's not as easy for the charges to go through there. When you buy a 100-watt light bulb, which is very bright, it has very low resistance, and therefore it's easy for charges to get through there and lose their energy to heat. So that's one thing that is complicating buying light bulbs, is to understand that the inherent property that you're really buying is a certain resistance of bulb. That's what you can count on. If you plug it in as recommended into a standard outlet and don't have it on a dimmer, then you can count on that resistance producing that power. Okay? So that's one complicating factor, and this is just for the old school incandescent light bulbs. Here's the thing though. When you have a 100-watt light bulb, the way that an incandescent bulb, an old school incandescent bulb, it completely works by brute force. What it does is that it makes something so hot it happens to partially glow, just like the stove, right? When it gets hot enough, it glows. So just as an example, that is the total power output. That may be going, say, 20 watts into actual light energy, and maybe 80 watts into just plain old heat. Basically, this is visible light, and this is what we call infrared, or IR. So it's mostly waste. Okay? The 100 watts just indicates how much total energy is being outputted. Only a small percentage of it was actually visible light. The rest of it was heat, and if you've ever accidentally touched an incandescent light bulb when it was either on or had recently been on, you know that is a lot of heat generation. Now, that's great because an old school incandescent light bulb was a great joint light and heater. So if you had a cold apartment, it did double duty and did both things. But it's a different story when you simultaneously have the air conditioning on. So if you want light bulbs to just generate light, the second thing that they outputted, heat, was really kind of waste. So this is where we have the modern generation of more efficient stuff. In fact, I believe it's illegal now to sell an incandescent light bulb in California. Okay? I think there's still a couple people that are selling them with a loophole. They're saying they're joint light bulbs and heaters, which is true. That's totally what they are. Okay? But this just further convolutes the shopping for light bulbs. Like, I know for me, I have a sense from growing up, how bright is a 100-watt bulb, right? How bright is a 50-watt light bulb? So I go to the store and that's what I'm looking for. And they're able to indulge someone like me, because I look and I see like a 20-watt light bulb, I'm like, who wants a 20 watts? It's so dim. But it's just as bright as a 100-watt bulb. It's just more efficient, right? They just figured out a way to dump out the same 20 watts of light without having the 80 watts of waste, right? So if you look, light bulbs, they're sold two different ways. This is like this weird crossover period. Some of them will say 100 watts on it, and then it'll say 100 watt and then small print equivalent, actually 20 watts. Okay, so sometimes they'll say, here's what you think this should be, but actually it's only 20 watts, but it's more efficient. I've also seen some brands where they put, this is 20 watts, and then the small print 100 watt equivalent. So it's just, which one do they prefer? Do they prefer to tell you what it really is, or to, in the fine print, or what you think it should be in the fine print? Okay. So does that make sense? Okay, so any light bulb box that you have laying around that you've bought recently, it has something to this regard somewhere. Okay. Okay, so that's a little bit about power. Now we're ready to build some circuits. So we've got these three. That's all we need. Let's do it. I'll do them on the board first, and then I'll go ahead and build them here for you. We can watch them on the table. So first I'll do what I'll call a simple circuit. And the simple circuit will just be a single battery with a single resistor attached. So this will be a 12-volt battery, which means that one terminal is 12 volts higher than the other. I should tell you we have a special character sometimes for the voltage difference of a battery. That's called the EMF, and we use the Greek letter epsilon for that. There's no reason to worry about that. Just think about it as a characterization of the total voltage difference that's available in the circuit. The battery sets that. It sets the very top and the very bottom. We have a resistor in here, and the resistor, let's say it's, I don't know, let's just make it 1 ohm. Nice and simple. So let's calculate for this how much current will flow and how much energy lost per time to thermal energy will we get. Question?
What does the E stand for?
EMF. Do you want to know what EMF stands for?
No, the E.
EMF.
EMF.
Yeah, EMF is a special letter we use to denote the voltage difference across the battery. EMF stands for electromotive force, but you didn't hear that from me because it's not a force, it's voltage. This is just people didn't know what they were talking about. They came up with stuff. Okay, so let's talk about how to do this. Well, for us, we take that the battery terminals and the wires connected to it are an equipotential. So the wire just allows us to extend the equipotential plateau all the way to where the resistor is. This is our higher voltage equipotential. And then similarly, we have the lower voltage terminal of the battery and any contiguous piece of wire connected to it. That will be our lower voltage equipotential. So the only way to traverse from the higher voltage to the lower voltage is to burrow through this resistor. Again, remember that we take the current as being the flow of positive charge. So the current will go like this. Remember that it is entirely, the whole system has charge carriers filled. The whole system is filled with charge carriers, and the moment we connect the battery, they all start moving in a line, okay? Like the American Idol auditions, okay? It's not like they flow through and get surprised. They immediately sense how much resistance is in the entire circuit, and then they flow accordingly. And that amount, we can calculate, I equals V over R. So the voltage difference across the ends of the resistor, 12 volts. The only reason a charge would go through that obstruction is because it has an energy reward. It goes to where 12 volts lower, and the amount of obstruction in the way is 1 ohm. So we get, this is 12 amps. So that means 12 coulombs will flow through there per second. That is an unhealthy amount of current, but it's a nice round number. Okay. You do not want to be messing with 12 amps. Don't touch something that has 12 amps in it. And then let's calculate the power dissipation. We can really use any of the equations that we have. I guess it's maybe slightly nicer to use the last one just because if I miscalculated the current, then it's going to mess me up here. So I go ahead and I put in 12 volts, motivation squared divided by 1 ohm, and I get 144 watts. So in this particular resistor, we will send 144 joules of energy from potential energy out per time, and that will be, if it's a normal resistor, it'll mostly be heat. If it's a light bulb, part of the small fraction of that maybe come out as light. Okay. I guess I should mention that for any given light bulb, the power will be our rating for brightness. Okay. Any given light bulb, the brighter it is, the more power is dissipated through it. When you take the dimmer down, it dissipates less power because it's less bright. Okay, so that's pretty straightforward. For comparison's sake, let me put another circuit here. I'm going to take the same battery, 12 volts, and I'm going to again connect one resistor, but that resistance is going to be bigger. It's a bigger obstruction. So I'm putting a bigger obstruction in the way. So just intuitively, just conceptually, should I get more current or less current? Less current, right? Put a bigger thing in the way, it's not going to flow as easily. And indeed, if you work it out, it's only 6 amps. So less current flows because there's a bigger obstruction in the way. The motivation is the same. We put in a 12-volt battery, so that's how badly charges we want to get through there. But motivation being the same, 12 volts, but the resistance being larger, the current is smaller. In the limit that the resistance is infinity, how much current we get? 0. So that's when you turn the dimmer all the way down to 0. You're basically setting it to be such a high resistance that nothing can get through. We can, of course, calculate the power here as well. And because it's a smaller resistance, it will also dissipate less power. That will be only 72 watts. So that's less as well. If you want, you can think of it just in terms of this, right? We talked about your power dissipation comes from how much energy is lost per charge and how many charges flow per time. Well, 12 volts, right, is the same in both of these. This is a 12-volt drop, this is a 12-volt drop. And that 12 volts is how much energy loss we get per charge. So that's not the difference. What's the difference? Why do we get less energy dissipation in the second resistor? It's not the V, but it's the less of them, right? So one way to think of this is that we get every single charge that goes through here, you have the same energy loss per time. Energy loss per charge. That's the voltage. But there are just many fewer of them. So fewer charges per time. So the current is smaller. So if you have that V is the same, but I is smaller, of course, that means that the total energy loss is smaller as well. Okay? So this is same, but if this is decreased, then this will decrease.
Question, sir.
Yeah.
So, you know, I heard you saying the energy, potential energy equals like the thermal per time. That's the heat coming out.
Yes, so this is thermal energy, and a small part of that may be light energy as well.
So looking at the power for the one resistance, 1 ohms. So the power produces 144 watts.
Correct.
And the second one, the power produces 72 watts.
Yes.
So which one will be brighter then?
This one will be less bright. This will be more bright, right? Remember, the power is tied to the brightness. So if we were to compare these two bulbs, this would be brighter and this would be less bright. So we could draw that here or write that. This is brighter if it's a light bulb, and this will be dimmer. Oh, and I said I would look it up, so I'll try to do that.
So we can, I'm sorry.
Uh-huh.
So we cannot look at the power to say how much going into light, how much going into heat.
That's right. So it's beyond the scope of the course for me to ask you to calculate how much of that total is going into each form. But the thing that you can count on is that if you have a given light bulb, the fraction at which it dumps to each one is going to be about the same. So if you, for instance, have a given light bulb, or a given type of light bulb, let's say incandescent, you can assume that if it's dimmer, it's not because this ratio is different, it's because this total is just lower, right? So this is a discussion that I just wanted to point out to you as like a practical everyday thing. But basically think of it as that whatever, for an incandescent light bulb, we're looking at this total number. And if this total number is lower, then we can assume that this number is going to be lower as well, because it's always going to portion out its energy in the same way, right? So if we calculated that the total light, if the total thing from our equation was 80 watts, well, we probably, or let's not make it 80, let's make it 50. What we probably assume is that this would be 10 and this would be 40, right? So we assume it apportions it in the same way. So again, if we look at this, it's going to be dimmer. So we basically just use this number as a proxy for brightness, right? Does that make sense?
Yes.
So different types of light bulbs can proportion this differently, like the more energy efficient ones can do it differently, but for us, we're going to assume that light bulb is the same type in our circuits. So these are just two different they're light bulbs of the same resistance, but they're the same type of construction. So they're both going to divert the same amount of this 144 and 72, the same percentage of each goes to heat versus light. So since this is less overall, it'll be less bright. Does that answer your question?
Yes.
Yeah. Any other questions? Okay, so I guess let me hook it up first. Here I have a car charger. I'm using a car charger for reasons I'll get into later. Don't mess with this. This can put out 350 amps. Okay. And then I have these basically conducting poles. That's just basically so everyone can see it. So what I'll do is I will connect the red clamp here. This is the higher voltage, and I'll connect it here at the base. I need something to hold this down. Does someone have an object that's relatively heavy and that's perfect and small? So that basically extends the equipotential, the higher voltage equipotential, through the whole thing. It's all conductors. This is all just the higher voltage equipotential. And then the black clamp is the lower voltage. And if I connect it here at the base, I don't know what's going on there. There's a lot of, someone have anything heavier? Oh, thank you. So, I don't know why this has a lot of memory here. Let's do it like that. So this is basically extending the lower voltage equipotential here. Okay. So let me pull out a resistor. I'm not going to have 1 ohm and 2 ohm here because those are really low resistances and the current would be way too high. I don't want to mess with it. But I'm going to pull out something in roughly the same ratio. So I'll have R and 2R. Okay. So this will be R and this will be twice that. Okay. So let's go ahead and connect them here. I'll put the R here first. I guess I'll put the R first. Put it here, like so. I can connect it anywhere I want because it's an equipotential. And by the way, the higher resistance is basically right here. So this here is still part of the same equipotential as here. That's all one plateau. And then this whole thing is the lower voltage plateau. Okay. So I connect it, turn it on, and okay, it's a light bulb. So I'm sure you've all seen that before. Try to get a mental snapshot of how bright it is, so how blindingly bright that is. And then I will attempt to connect a resistor, which is twice that much, and we're expecting it to glow less brightly. So this should be slightly less blinding. Okay, that may be hard to see. but I guess I'll do it. So we're expecting this to be less blinding. Does it look slightly less bright? I guess. Problem with this one is that it's super bright, but it also has frosted glass on it, so it kind of makes it hard to tell. But this, hopefully you can see, is slightly less blinding. Okay, you can sort of see the internal construction of the thing because there's not so much light that the whole thing is just blown out. Okay, so there we have our 2 light bulbs. I know that's not a terribly compelling evidence, but the power dissipation, being indicative of brightness, is basically the only thing we have to go off of here, because I'm not going to hook up any voltmeters or what we call voltmeters, which measure voltage difference, or ammeters, which measure amps current. So the only thing we have with the naked eye is just looking at the power dissipation, and we see if it's kind of as we expect. So what's going to be more compelling is what I'm going to be doing next, which is I'm going to connect the same 2 resistors to the same battery, but I'm going to do them in combinations. So I'm going to do them in a row, which is called a series circuit. So charges have to go through one and then the other. And then I'm going to put them side by side so you can go through one or the other, which is called, again, it's called parallel. So again, that's what we're doing next. Series, you have to go through one and then the other, and parallel, where you have to go through one or the other. Okay. Okay. So any questions before I started on the series circuit? All right. So let's do the series circuit. I'm going to have the exact same 2 resistors, the 1 ohm and the 2 ohm, same battery, 12 volts. I'm just going to hook them up together. And as I do this, I am going to develop a series of things that I can count on for each type. This I will release to you shortly as a summary sheet as well, so you can kind of see all of these things there. So let's talk about a series circuit. Same battery, 12 volts. Same 2 resistors, a 1 ohm and a 2 ohm. But they're going to happen in a row. So this is R1, which is 1 ohm, and R2, which is 2 ohms. Okay, so this is our first circuit where you have to remember that the entire system is pervaded by charge carriers, and they will sense that there is a 1 ohm and a 2 ohm obstruction in the way, and they will flow accordingly to that knowledge. So it's not like you flow through one and they get totally surprised by what you run into. So the entire current is established based on what is in the way. So there will be current that flows from higher to lower voltage. It's a hypothetical movement of positive charge. And that current will be the same. There are no forks in this river, okay? So the amount of charge coursing through one, the amount of coulombs passing through one resistor per second is the same as through the other, okay? So that's one of the first things in series, is the current is the same through each resistor. There are no forks to this river. The amount of current that flows through each one is exactly the same. It's not like it can flow through the first one, get surprised by the second resistor, and then slow down. That's not how it works. It already knew that that second resistor was there. So the order of the resistors is irrelevant, okay? Doesn't matter that one is first and one is second. It knew about everything before it started to flow, okay? Now, the one way you can think about this circuit is you can imagine that the amount of resistance that is in the way can be encapsulated into one total, or as we call it, equivalent resistance. So this entire circuit will present an equivalent amount of resistance to some single resistor, okay? So there is some single resistor that will prevent as much flow as these two do together. So that's one of the things we will often do is we will take this and imagine replacing the current, or sorry, replacing the more complex multiple resistors with a single equivalent resistor. All right, so let's take a look here. This current, I guess I could call this I total. That amount of current that would flow in that equivalent circuit will be, from Ohm's law, just the battery voltage divided by the amount of resistance in the way, like so. So let's go back over here and look at my more complicated circuit.